recording is done. Here today we'll wrap up this semester with the follow-up from Thursday, virtual memory part 2, right? And a quick recap from Thursday. On Thursday we talked about 32 bits x86 page walk, right? So let's say you have an address in a 32-bit 32-bit machine. An address in 32 machine is going to contain 32 bits of data. I mean, of the address data, right? The last from the x86 page walk, right? One thing that you can get is the last set of bits is for the page offset. So if I use 12 bits, so over here is 12 bits for the page offset, how big is the page here? Can someone tell me how big is a page in x86 if my page offset is 12 bits? So what's the page size? Okay, right? So how do you get this? Page size is basically 2 to the number of bits for the page offset. 2 to the number of bits in the page offset. In this case, it's 2 to the 12. That's 4K. All right. So now we have 12 bits for the page offset. How many bits do we have left? 20, right? Because we start with 32 bits. We already used 12 bits, so you now have 20 bits. You basically can split that into half, right? Over here, you have the first half page directory, which is the first level, and the second level, the page table. You would use whatever numbers in the page directory right here. Whatever numbers represent here, you use that as an index into my table. In this case, let's say the number is 3. If this case, the number is 3, you go and look at the entry row number 3. Row number 3 will give you the page table entry. The page table entry contains 2 pieces of information. The first piece of information will tell you where is the next page table. The second piece of information will tell you some status bits that are related to that page. We will talk about this in a bit with actual real example from Ajahn Piti. I guess to be precise, Ajahn Piti's MacBook, right? But with that, we have the second level of the page table. Again, we use the index bit. So let's say this number is 4. Then you go to the entry over here, level, here. So there was a question on the chat. Why is so there are 2 questions, I guess. Why is the size of the page 4K? Is that the first question? Oh, why does it only contain 1024 entry when the size of the page is 4K, right? Oh, okay. So if I use a 32-bit machine, how big is my page table entry? How big is my page table entry? Okay. For the entire table, right? For one row, how big is that? I use 32-bit machine. How big is that one row? It's gonna contain 32 bits. It's actually contain 32 bits. In that case, 32 bits, how many bytes is that? 32-bit divided by 8 is 4 bytes, right? So, sorry. Yes, 32-bit divided by 8 is 4 bytes. So in that case, each entry is 4 bytes. The total size 4 kilobytes. So how many entries can I have? So it's 4096 divided by 4. You get 1024. So you can go up to entry number 0, row 0, to row 1023, right? You can have 1024 entry in total. That's why in this case, if you want to make sure the page table fit within this one page, the 4 kilobyte page, you can go up to 1024, and it actually fit perfectly because we only have 10 bits for that. You are going to end up with only 1024 row of page table entry. So hopefully, does it answer your question? All right, awesome. So yeah, so now that we established that this table has limited size, right? So we can use these index bits to go into what row we are accessing. In this case, second level, you go to the fourth row because the index bit say the number is 4. Once you're there, you take the page, the physical page number, which is this part. This gives you the physical page number. You append that with the page offset from the virtual address. Then with this, you get the page, not the page, you get the physical address. You get the actual location of that data pointed to by your virtual address, but now in DRAM, right? So these are the 32-bit x86 page walk. And the question we had earlier that get asked is why do we have 1024 entry? Is a perfect question that goes into the 64-bit x86 page walk. For the 64-bit x86 page walk, you have the same 12 bits offset, right? 12 bits offset, but do you notice something different about the other 4 levels? Do we use, how many bits are we using right now? How many bits? So with 12 bits, right? With 12 bits is 4 kilobyte page. We use 9-bit here, 9-bit here, 9-bit here, 9-bit here. So with 9 bits, how many rows do I have in the page table? How many rows do I have in the page table? It's 2 to the 9, right? 2 to the 9, so 512 rows. Why is that the case? If you have 4 kilobyte page, each address is 64 bits. Each address is 64 bits. So one row of the page table, how big is that? How big is one row in the page table if that's the case? So each row consumes 64 bits. So how big is that in the unit of byte? How many bytes are in 64 bits? 8 bytes, right? So that's one row. That's one row. With the 4 kilobyte page, how many row can I have? With 4 kilobyte page, how many row can I have? It's 8 bytes per row. You have 4 kilobytes in total. So what's the total number of row? 512, right? 512 is 2 to the 9. That's why in this case, it's not 10 bits. We use 9 bits here. Because one page table is only now contain 512 row. The reason why it's 512 rather than 1024 is because each row is doubling the size. From 4 bytes is now 8 bytes. So that fit perfectly with one page. All right. So that's a subtle difference here. But the everything else stay the same. The way page walk work is Intel and AMD processor would have this register. It's called CR3. CR3 is a special register that points to your first level page table. Well, let me call this level 4 because we have 4 steps. You start with level 4 page table. You get the index. The index tell you what row you're accessing. That row will give you the address of the next table. You use index number 3 to index into this table and see what row do you go to. And then that row give you the next table. Now, once you're in level 2, there's something pretty neat that is available in, for example, Linux and I'm not sure if whether Windows has this or not, but in the level 2 table, Linux, in particular the Linux THP, is called huge page. This allows actually your machine to operate in a much bigger page size. Rather than a 4 kilobyte page size, you can use the physical frame number, which is this part of the PT. this part of the PTE as your physical frame number, and then your page is now 20 bits, 21 bits long. 21 bits long means that your page is now 2 megabytes. 2 megabytes. You basically combine this part together. That becomes the page offset. But most of your machine, if not all, like all your computer right now, doesn't enabling this all the time. Most of the time you don't enabling it. You would go to the next level to go to the 4K granularity. Basically now your page is 4 kilobytes. Physical page number is in the last, so we use 12 bytes for that. So the last 52 bits become the physical page number. The rest are the permission bits. Anyone remember what do we use the permission bits for? These are the status bits that I said earlier. What do we use that for? So what is one of the old friends that you've seen all the time in your debugging C program that you're probably so sick of it by now? Is checking if you can access the data or not. If you cannot access the data in your program, you're gonna get things like seg fault, right? So that's what the permission bit is for. We sometimes call this the protection bit, right? So let me give you first. Let me give the credit to Ajahn Piti so for sharing with me his one of the error that he ran into when he was using his MacBook, right? So there was a post back in October 20 of this year. I think almost exactly 1 month ago, he was posting this on his Facebook page. He say, "Hey, I was coding and the crash caused like 3 lines to be gone." I think was using the one of the M1 chip on MacBook, but definitely on this is on Apple computer. But the same error can happen on any single OS. It can happen in Linux. It can happen in Windows. It can happen on Intel and AMD processor. Because if you look at the error, how many of you here actually check out the error code whenever you get something like this? But can you see the screen quite? I know it's a little bit small, but do you see the screen? Okay, so yes. So one thing that you can check is you can take the error code and you can Google for that. But if you look at this, that's actually a hint of what's going on. So the first hint that I'm gonna circle in here is this thing called SMMU. This SMMU. Remember something that's called MMU from our lecture? The memory management unit. What are they responsible for? The MMU. This thing is used to handle page walk. What is a page walk? We use the MMU to handle the page walk. So let me ask you this question. What's a page walk? Why do we need a page walk? We use it to get my physical address, right? We use it to get the physical address to be able to locate our data, right? Another hint here is you see PTE invalid exception. PTE. Anything that remind you about the lecture when you see the word PTE? Page table entry, exactly. DVA, read with DVA, this is the virtual address. Basically, the error code is giving you, hey, this is a virtual address I'm trying to access. It's go through the PTE. And somehow, I don't know what, the machine doesn't know what happened, but the permission bit tell me this is an illegal access. This error code can be generated. To be honest, this thing can be sent to Apple so that they can basically hopefully fix this bug, right? Basically, something is going on. you're trying to access the data, but you walk the page table. It turns out the page table entry, the status bit, tell you something is wrong with this access. You have no permission to access it. The source of this can happen from multiple things. It can be like, for example, the driver code trying to access it, but there's a bug in there. It has a wrong virtual address, so that when you go through the page table entry, it's wrong. It can be the OS didn't initialize the page table properly, so when you go through the page table entry, it's wrong. So many things can go on. That's why the error code contains all these information, so that the engineer at Apple can come in and like, okay, this might be what's going on, so I can patch it. From what I've seen, it's still like quite a lot of these error on their computer. So there might be multiple things that are going on. Some of them are likely being patched. Some of them are still trying to make sure they can be patched so that this thing doesn't happen as often. This is the same thing as, like, for example, sometimes you run into blue screen, right? How many people run into blue screen on your Windows machine? Or how many people are running something on Windows and sometime out of the blue, the program does crash itself? This also includes segfault, right? The program crash itself. So these are some of the protection that DOS actually give it to the user while they are bad, as in like you lose work or you lose a game or you lose that match while you're playing some game, right? It's still better that you go and randomly change kernel data or make your computer like basically destroy your computer by writing some invalid data to some protected region in the main memory, right? So these are what's going on. All right. Now we talk about what virtual memory is designed for. And this is one of the main goal, having this permission bits, right? But what are the overhead of having virtual memory, right? The world is not perfect. Sometimes you want something, you have to pay the price. So what's the price of deploying virtual memory? The performance overhead of virtual memory. Recall that page table are in DRAM, right? Recall that the page table are in DRAM. And from our caching lecture, DRAM takes a long time, right? DRAM takes a long time. So what we want to do is to go to the DRAM as basically not as often as possible. We want to avoid going to DRAM because that's a long process. And from our page table structure, right? You know that to get the physical address, you have to go to DRAM multiple times. In the 32-bit machine, you go to DRAM twice. In a 64-bit machine, you go to DRAM 4 times. That's a lot, right? So the overhead of this is if you have 4 levels of the page table, you need to access the memory 4 times in order to actually know what's my physical address, right? The first problem then is if you want to get something from DRAM, you need the physical address. Your processor only have the virtual address. So you cannot get DRAM. You cannot get to DRAM because you don't have the address. This is like when you want to go using Google Map to search for some restaurant, right? But you don't have the address of the restaurant, so you cannot search. In this case, in the computer, you would have to go through the page walk process and access DRAM 4 times before you now have the address. So that's the first problem. The second problem in many modern processor, right? In many modern processor, sorry about on Wednesday. We are going to talk about this right now. In many modern processor, you cannot access the cache without knowing the physical address, and we'll talk about this in a bit. We'll talk about this in a bit, but let's go through the first problem. Let's go through the first problem right now. I want to access my data in DRAM. I don't have the physical address. I only have the virtual address. So how do I fix this? So right now, this is the processor side. The processor have right, have virtual address. And then if you look at DRAM, to get the data, right, DRAM, I need the physical address. So if you break down the physical address, you basically have the physical page number and the page offset, right? And if you break down the virtual address, you again have the virtual page number and you have the page offset. These page offset are the same information. These are the same. But the virtual page number has to be decrypted into the physical page number. And that's something that we learned already in the past, maybe 4 lectures ago, that can be used to help this. Anything we can do, let's assume that we can change the hardware. I mean, why not? We build computers anyway, so we can change the hardware. We can design new computer. So let's say I have a computer that still suffer from this process. What can I do? Can I use some concept we just learned to fix this problem? Any idea? So what structure can be used to avoid going to DRAM? What structure that we just learned in the past couple of weeks that we can use to prevent you from going to DRAM? A cache, yes, perfect. I can use something like a cache, right? This is another uh, um, way I can use the concept of the cache, right? Yeah, but you don't have the physical address. That's what you want, right? So the solution is actually called translation leukocyte buffer. This is the terminology that we all use. It's called the translation leukocyte buffer, or the TLB. The way I would remember this is basically a cache that takes virtual page number and give physical page number. All right. As simple as that. I have some caching structure, right? I have some caching structure that store virtual page number. You search using virtual page number because that's the information that the processor have. It throw out the physical page number. So for any commonly used address, you can use, say, for example, the LRU policy, the least recently used policy to manage this and maintain the list of physical page number you want to store in the cache, right? And similar to the data cache that we learned from the caching lecture, there can be multiple levels of the TLB, a small, really fast TLB, and a larger share level 2 TLB that's shared by multiple processors. If it's a TLB hit, you can return the physical address right away. If it's a TLB miss, you now have to do the page walk, right? So is the concept clear? I am using some caching structure to store frequently used page. So if I want to do that, what should be in the structure, right? If you look at caching, right, that's a part for the tag, right? And that's a part for the data. I have virtual address as an input. I want physical address as an output. Virtual address can be broken down into VPN, the virtual page number, and the page offset. Physical page number can be broken down into the physical page number or the PPN and the page offset. The page offset are the same in virtual address and physical address. There are multiple rows in here that you can store the data and the tag. So what should go into the tag? What should I put in the tag? Actually, it's the simplest one. What should I put in the data? What am I trying to cache here? What am I trying to cache? You have virtual address. What do you want out of it? What do you want? The physical address, right? So the simplest thing you can do is put the virtual address in as a tag, as a key, and you get the physical address. But then, because page offset are the same, do I need to put in the physical address, or is it okay if I put in just a physical page number? Is it okay if I just put in the PPN? I mean, I already know the page offset, so I just need to put it in the PPN for my data, right? So over here, I can put in the PPN. And what do I use to search? What should be in the tag? So actually not the page offset, because you already know the page offset for the physical address. You want to be able to tell what is the physical page number that VPN number one map to. You want to be able to tell, okay, I have this virtual page number. What is my physical page number? So for the tag, you would put in the VPN. By the way, VPN stands, in this case, stand for virtual page number. It's not the virtual private network. The VPN you use for other purposes on the networking side, this is a different concept. This is VPN that stands for virtual page number. It's the page number for your virtual address that can be translated to the page number for the physical address. All right, is this clear? So if you have the VPN2, for example, you go search and it results in PPN2, then you know the physical address, because the physical address is essentially PPN2, and then you append the page offset next to it, right? Your physical address is basically, right, PPN again, and append with the page offset. Okay. All right, so let's take a quick break here. Let's take a quick break here before we go through the next set of problems. Before we go to the next set of problems, because the next part typically is the one that confuses the students the most, at least based on my feedback. So I'm gonna do a pause here for 5 minutes, or actually let's do 8 minutes pause. We'll resume at 2:55. All right, we'll resume at 2:55. In the meantime, feel free to type in the question so that you can when we come back, I'm gonna go through the questions in case something in here are confusing. All right. All right, now that we are back from the quick break, we will talk about the second problems. In many modern design, right, you cannot access the cache without knowing the physical address. And what do I mean by this, and why does it happen? The reason why this happens is first need to look into the caching lecture, right? So we talk about the cache in the context of you have the address. You have the address. In the address, before you access the cache, you would have some bits set aside for the byte in block bits. These are used to tell what byte inside the cache block. What byte are we trying to access here? Quick note, you need that for assignment 4 as well. Make sure you know how to do this. Then the other two information are the index bit and the tag bits, right? But I actually never tell you for this address, this address, is this virtual address or is this physical address? Because by this point, you have two notions of the address, right? My address can be something the computer program see. Inside your program, the pointer are virtual address. So the address, the processor, the CPU, the address that they see is going to be the virtual address. But the address used by DRAM, that's a physical address. So what do we use here? Anyone want to take a guess on should we use virtual address or should we use physical address? What should we do here? So let's go with that question, right? Let's go with that question. One thing you might have noticed is you have a choice. You have a choice to search and use the cache, right? So, okay, that's a comment on the chat. Great comment for sure, right? Virtual address actually seems easy to manage because you already have it. But PA, once you have the physical address, it seems more logical, right? If you think about this, physical address is your location in DRAM. You already use it to tell if that's your address or not in DRAM. So we should be okay using the physical address for the index and the tag. But the CPU has a virtual address. It seems more intuitive in terms of performance if we can use virtual address, right? But you have a choice. Yeah, you have a choice. And because we are all designing a computer, right? I mean, we are still doing it even now, right? That's actually the way I can justify my existence if I joke about it. Like I'm a computer architect. So my existence is I'm gonna keep inventing and building new type of computer, right? That's what we do. So put that hat in, right? You have the address that are being used to access the cache. And you have the virtual address, you have the physical address. Basically, it means that you can use either of them, and you have 4 choices in total. The first choice is I use physical address for everything. Physical address for the index, physical address for the tag. I can use physical address for the index, virtual address for the tag. I can use virtual address for the index, physical address for the tag, and I can use virtual address for everything, right? So now are we all on the same page? There are 4 possible choices, and we'll basically clear this up and ended up with only one resulting choice. So right now we have 4 possible choices. I can use physical address for the index. I can use physical address for the tag. I can use virtual address for the index. I can use virtual address for the tag. Let's look into some of these and see if we are going to run into any problems. The first problem I'm going to talk about is called the homonym problem. Homonym problem, the way you remember this is easy. I have two programs. By accident, they have the same virtual address. Is that possible? I run 2 programs. By accident, the OS hand them the same virtual address. Yeah, it's possible because these are virtual address. These are just fake address that I can name. I can name, say, favorite restaurant 1 and favorite restaurant 1 by mistake on Google Map, right? The same virtual address, but it actually points to 2 different restaurants, right? So this is what can happen. I have the same virtual address, but because they're from 2 different programs, they would map to 2 different locations in DRAM, right? This is called the homonym problem, and is this problematic? Is this something we have to ensure this has to be taken care of? So between the index and the tag, which one are being used to tell is that your data or not? Do I use the index for that, or do you use the tag for that? You use the tag, right? So if you already forgot, here's how I would remember this. The easiest thing I can do is I'm gonna compare the cache to going into the movie theater. When you go into the movie theater, you have rows of seats, right? And you have a movie ticket. You need to tell where is your seat. If you go to the theater, the row is the index. Then to tell whether that's your seat or not, you use the seat number, that's the tag. So ultimately, you are going to use the tag to tell is that your address. So should the tag be virtual or physical in this case? Because I have the same virtual address, but 2 different physical address. To make sure I can access the correct data, should I use the virtual address for the tag, or should I use the physical address for the tag? the physical address, right? Because that's the only way I can tell the difference, right? That's the only way I can tell the difference. I need the physical address for the tag. So now let's go back to the slide where I have 4 choices again. Which one can I get rid of? I can get rid of anything that use virtual address for the tag, right? So if you're curious, there has been proposal to use VIVT, and that's actually a clear benefit in terms of performance. We are not going to talk about those solutions because it's a little bit too advanced, and it kind of requires you to hack the kernel, hack the OS to make this possible. But for now, I will make sure that the tag is the physical address so I can access my correct data. This is for correctness issue. So you only have 2 choices left, right? Between PIPT, I use physical address for everything, and VIPT, I use physical address for the tag, and I use virtual address for the index. So let me talk about the issue with PIPT. There's no correctness issue. This is more of the performance issue. This is more the performance issue. To use the PIPT, what information do you need? Do we need physical address for everything? Do we need physical address for everything? The answer is yes, we need physical address for both the index and the tag. This means that before you even touch the cache, before you even get to touch the cache to try to search for your data, you need the physical address. So here's what happens when you use PIPT. You start with the virtual address. Right? So what's the first thing you check to get your physical address? What's the first thing you check to get the physical address? So what's that cache for virtual address called? Well, before that, because we need the physical address for the index. So we need to first get my physical address. How do I get my physical address? What's that thing that cache the physical address information? The TLB, right? We would first search the TLB. And if it's a TLB hit, what do you get out of this? What do you get out of this? The physical address, right? So with this, you get the physical address. I'm going to change the color to blue because now we have the physical address. Then once we have the physical address, we get the index bit, right? What does the index bit give you? What does the index bit give you? Actually, it gives you the cache set. It gives you the cache set. It gives you the set ID, right? So now you have the cache set, right? With the cache set, how can you tell whether it's your data or not? What's the next step? So now you use the index bit to get the set. What's the next step? How do I know whether it's my data or not? You check the tag, right? Check the tag. So let me assume some number. Let's assume that searching for the TLB take 1 clock cycle. Then getting the cache set take 1 clock cycle. And then checking for the tag take another clock cycle. How long does it take in total over here to actually see if my data is in the cache or not? 3 cycles, right? So over here, the whole process takes 3 cycles. This is okay. This is actually okay. But I will then talk about another approach that can cut this into just 2 cycles. Seems small, but that's 50% faster, right? 50% faster is really, really, really good speed up. All right. So let's talk about VIPT. VIPT is you can look at this observation, right? You first try to get the physical address to get the set, then use the set information to compare the tag. So the reason why PIPT, the physical address for the index bit, cannot get the set ahead of time is because I need the physical address for that. So is it okay if I use the virtual address for my index bit? Is it okay? So let's first ask this question. Can I use virtual address for the index bit? Will I still get the correct block? Which information between the index and the tag, which information do I need to use to tell whether it's my data or not? Do I use the index or do I use the tag? At the end of the day, we use the tag, right? So as long as physical address is used for the tag, I'm okay to use virtual address for the index bit. It's totally okay. So what's the benefit of this? I have my virtual address. Right? Sorry, I will use the same color coding. So I'm going to use blue for physical, red for virtual. So I have virtual address. With the virtual address, what can I do? I can do this. I can use the virtual address to get the set. And at the same time, can I use the virtual address to check the TLB? Can I do these two things in parallel? Because I have the information, so I can do it, right? So with this, right, once you have the set, then you compare the tag. Right? So this, again, let's assume the same assumption. This take one cycle. This take one cycle. And this take one cycle. But how much time in total do I need for this? How much time in total? Yes, you only need 2 cycles, right? So you cut the time by 30%, just doing this. In reality, the benefit of VIPT is pretty significant. Sometimes, I mean, the looking up the TLB would take like 2 to 4 cycles, getting the set around the same amount of time. So when you can overlap that process, you gain that benefit. All right. So the benefit here is you overlap the lookup, getting that set and the TLB lookup in order to get your physical address. You overlap that process. You run that in parallel. You perform the 2 things in parallel. Then you can still use physical address for tag checking, which is good. The only downside is, well, you want to make sure that you hit in the TLB, because if you miss in the TLB, it's not much you can do. You have to do the page walk. All right. Any questions so far? Because if not, I will wrap things up. And look at a day of life in the data access. So let's say I have print F, and then I do *I over here. What am I trying to do here? Okay, let me put it in a more correct syntax. So let me write a proper C syntax. Print F %D *I, right? In this case, I is an address. I want to print what? So let's say this is in DRAM. Everything, I'll swap the color. Everything in red here is physical. Everything in blue is virtual. All right. This is where I is, and I want to print whatever the value is right here. You are printing the value, right? It's a load. Load value at address I. Are we all with me so far? That's what we want to do. That's the only thing we want to do. One line of code in C. We'll look into what happened. All right, yes, no. Are we all on the same page with the beginning of this example? Because there'll be both the caching structure and the translation structure. So now we have the code, right? Printf %d star I. Over here, you have the physical address for I. Physical address for I consists of the page offset and the physical page number. On the left side, when you look at the processor, you have the virtual address for I, which is basically the virtual page number and the page offset, right? So that's the processor side. In the caching structure, you have the cache, L1, L2, and last level cache. On the translation structure, you have the TLB and the memory management unit, the one that performs the page walk. And as we said, we want to just load the address, load the value at address I, right? Are we all with me so far? Any questions? Any questions? This is what we want to do. The processor received the command, go look at this address I and print that value. The location of I is in DRAM. Now I'll take you through this process. All right. So what should we do first? We have the virtual address. What should we do first? What should we do? So what's the first step here? We have the virtual address. Where do we start? Can I go and get that set from the cache? Can I go and get the set from the cache in the L1? Can I go to the L1 and grab the set that I want to search? I have an address, right? I have the virtual address. What do we use for the index bit? You use the virtual address for the index bit. So you take the index bit from the virtual address, go to the L1 cache. Can I also go to the TLB to get my physical address? Can I also do that at the same time? Yes, right. So you would also go to the TLB. If this is a TLB hit, what do you get? Can I go to the cache now and compare the tag? If this is a TLB hit, it means you have the physical address right away. So you go to the L1 cache saying, hey, that's my tag, go and compare, right? And that's it. You go look that up in the L1 cache using the physical address for the tag. All right. What if you have a TLB miss? What if you have a TLB miss? What would happen? You don't have to, you go to the MMU, yes. You have to go perform the page walk because you don't have the physical address. And if you don't have the physical address, there's no way for you to access the cache because you don't have the tag. So in that case, you go through the MMU. MMU go and get the physical address from the page table. So if this is a 64-bit machine, how many times do I have to go access the page table? How many trips to DRAM do I have to do? If it's a 64-bit with 4 level of the page table, how many trips do I have to do to DRAM? Exactly, right? 5 counting the last trip to get the data. But if you just want the physical address, you do 4 trips, right? 1, 2, 3, and 4 to get your physical address, which is now available here after you do the page walk. Now you have the tag. Now you have both the index and the tag. You check the cache. If this is a hit, if this is a cache hit, you return the data to the processor. Done. If this is a cache miss, then you go to the level 2 cache. If it miss again, you go to the last level cache. If it miss again, that's when you access the data. You then use the physical address to check, hey, where's my value in DRAM? All right. Any questions about this diagram? Any questions about this diagram? That's actually what happened under the hood when you have data access in your program. This is what happened in your computer. All right. Any questions so far? And that's it. That's a fusion of memory hierarchy lecture, caching lecture, and virtual memory lecture in one slide, right? So that's what is the key message out of this portion of the class. Why do we need this? All of these new hardware structure like cache and the TLB, they are being added to make sure your data access is really fast, right? Your data access is really fast. Any questions so far? Because then I'm going to talk about the last elephant in the room. This thing called page fault. How many of you run many programs where way too many programs that your laptop gets really slow? How many of you run into that scenario before? All right. Chrome is enough. Yes, I agree. Actually, Chrome uses a lot of memory in some cases. And yes, if you have 20 Chromes open, it's likely that you might be starting to see the slowdown already. Why is that the case? Why do you start to feel the computer get slower? So what's one of the possible causes? You are running out, right? You are running out of memory. Your memory is not big enough to hold all this like temporary value that all the programs want to use. So the one of the benefit of virtual address is to make sure you can have the virtually larger than DRAM, right? Larger than DRAM. So this seems cool, right? But how many of you question that if that's the case, why do I see the slowdown? Why is it still slow when you're running out of memory? If my virtual address can extend the size of your memory to be really big. The reason behind that is DRAM is limited. If you use more than what DRAM have, those pages, those data, sometimes they get stored in the hard drive, in the storage. This process is called the page fault, and the process of going to get your data is called demand paging, right? You do demand paging to get the data from wherever the data is located back to the memory. Anyone want to take a guess why is this a slow process comparing to just going to DRAM and access the data? Hard drive is a lot slower, right? A lot slower than DRAM. So I'm actually looking at the specification of basically current this is July 27 on my screen this year, right? If you look at the access latency of hard drive, to be honest, let's do SSD, like SATA SSD. you're looking at around 70 microseconds. You're looking at around 70 microseconds. Compare that to DRAM, which is between 12 to 50 nanosecond. How big of a difference was that? What's the difference between 70 microsecond and 12 to 50 nanosecond? Is that a big difference? It's 1,000 times worse, right? Because memory is faster, it's much faster than DRAM, right? So paging takes a long time. This takes a long time. That is why, right, despite the fact that your computer doesn't crash, the computer doesn't crash, but you're gonna see some significant slowdown, right? So that's something that virtual memory is giving you. The other thing that I already showed you earlier is memory protection. This is something that I'm going to call, using a more generic word called memory protection. When you do the translation, the machine actually checks the page table entry for the permission bits. If you violate that, you get exception. Things like what I showed you earlier on the M1 chip processor, or even Apple or Mac OS, where you get this error code and the program crash, things like segmentation faults. The reason behind that is these bits include things like the address space ID. Treat the address space ID similar to the process ID, but this one is for each address space that are being shared. It can be shared amongst different threads, right? Read and write versus read only. So if you want to write to a location that's marked as read only, that's a violation. User versus supervisor. User are not supposed to overwrite something or read the data from the supervisor region or supervisor's page, right? So again, these are the way to protect the memory, right? Think of it as this like a permission bits where it either allow you to access the data or say something's wrong here. I'm not going to let you access the data. All right. So that is it for the semester material. Anything I talk about from now on will not be on the final exam. All right. Oh, great question. Will the information that was in the swap space be gone when I close my computer, similar to how you use DRAM? Gone it will be gone in a sense that you should not be able to access it again when you open it up and you boot the computer up again. You should not be able to access them again. It's the choice of the OS to whether to clean it up or just leave it as is, and the next time you use it, you mark that as a region you can use. You can overwrite on it, right? Most of the time when you delete a file, from hard drive, it's actually not getting erased. You're just marking that region as you can overwrite that region. These are some junk data that you don't need anymore. You can treat it the same way. So the swap space, when you close your computer, the data can still remain there, but you should not be able to access it afterward because, I mean, there's no need to access it. All right. So before we leave today, one additional thing that I want to kind of show you about why virtual memory can be something that can make impact on performance, right? How many of you use virtual machine like VirtualBox before and you feel like it's slow? Anyone use virtual machine before? Or crash so many times you don't want to count. So one thing that make virtual machine a lot slower is page walk. So let's compare the page walk process here, right? So this is the guest OS, and this is the host OS. Sometimes we call this a hypervisor as well. This is basically your physical machine. And this is where your DRAM is. The guest OS, this is your virtual machine. And let's go through the same example. I have this int, right, star I, and I do print f %d star I. What am I trying to do here? If I have to do a page walk, what do I have here? I have virtual address, right? And at the end of the day, I want physical address. At the end of the day, I want the physical address. So to get the physical address, what do? You go to the PTE level 4. Then you go to the level 3. Then you go to the level 2, right? Then you go to the level 1. That's when you got the physical address. All right? Everyone with me so far? I am doing the translation. I'm doing the page walk inside the guest operating system. This is in your virtual machine. This is in your virtual machine. So for each of this, where are these things in my DRAM? So when you have page table entry level 4, this is the host virtual address 1. This is also another virtual address on the host, right? Are you all with me so far? Basically, every time I do the translation, I go through the page walk process. I go through the page table inside the virtual machine. But each of these page table location inside your virtual machine is a virtual address in your physical machine, in your laptop, in your computer. So if I have host virtual address 1, how do I get to host physical address 1? You have to do page walk again, right? You have to do the page walk again. So this is level 4, level 3, level 2, and level 1. So you do walk number 4, walk number 3, walk number 2, walk number 1 to get to the host physical address. The same thing goes here, right? Walk 4, walk 3, walk 2, walk 1. So with this one data access, let's count how many access to DRAM. How many access to DRAM that you have to do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, actually, I forgot something. My bad. It's actually even worse than this. 1, 2, 3, 4, 5. Right, when you have the physical address, you need to get the data. So then 6 here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that's when you get your physical address. From 4 access, you go up to 24. Is it bad? Just to do this, you increase from 4 access to 24 access in virtual machine. Is this a bad thing? It is actually horrifying, right? So if you look at current solution, there's multiple solution that has been proposed, and many of the work are trying to like squash that from 4 to 24. You become 4 to something close to 4 and 6, like 4 and 5 and 6, depending on the solution. So this is still quite active area of work that are going on. But the reason why I brought it up is this is actually one of the things that can happen and can be one of the source that virtual machine can be a little bit slower than running things on your own physical machine. All right. This is quite different if you use the current generation of virtual machine as well as when you use the things like Docker and container. So it's going to be different from this, but the key concept apply. You need to make sure you can translate virtual address to the physical address, but now you have the guest OS and the host OS. With container, you only have the host OS, so it's not as bad, but now you have a different translation structure tied to that, right? So it's a different overhead that comes into play. All right, so that's another like tidbits that I kind of want to communicate why address translation and page walk are still important for you guys to at least realize, right? Then the last thing we want to talk about today is let's discuss assignment 4. It just came out this morning. I want you to create basically a simple cache simulator. This is simpler than previous semester. This is based on the feedback I got. What you have is a starter code with the list of address that are provided as an input to your simulator and some starter code that you can play with. Your cache simulator would operate like a proper cache based on the input. Basically, the input at the list of address with the read and write information. You can process that and make sure that you can actually have a functioning cache being simulated in a program, right? So let's talk about this in a little bit more detail, right? The structure of your cache right now is 16-byte cache block, 2-level cache. Basically, this means you have the L1 and the L2 before you go to DRAM. You don't have to worry about DRAM. This is already in the starter code. So we have initialized the DRAM for you. You only have to build the L1 and the L2. I also kind of pre-built the way you can proceed and go forward in time, reading the input. So you don't have to worry about how do I read the input, how do I print the content of the cache. You only have to worry about the cache itself. The L1 is 2 sets, set 0, set 1, and it's two-way set associative. So you have way 0 and way 1. L2, instead of 2 by 2, 2 sets, two-way is 4 sets. Sorry, that's 5 sets. 4 sets and 4 ways. You have set 0, set 1, set 2, and set 3. So let's say you have 3 accesses, 3 read, for example, to the cache block. Do you have 3 read to cache block 1, then cache block 2, and cache block 3? And let's say that they happen to go to set 1 of both L1 and L2. So you put cache block 1 in here, cache block 2 in here, cache block 3 in here. You put cache block 1 in here, then the next access to cache block number 2. When I have read to cache block number 3, what do I do here in the L1? What should I do in L1? Well, yes, it's a cache miss, right? And then you want to insert cache block 3 in here, right? So how do I insert? I have only two ways, so how do I insert? Right now, we use first in, first out policy. This is a little bit different from the LRU policy we learned because this is simpler. If you go in first, you get kicked out first. So in this case, which one do you kick out to make room for cache block 3? Cache block 1, right? So you then get rid of cache block 1 and then you put in cache block 3. All right. So that's what we want you to do. We want you to be able to maintain the status of these cache when you have access to different cache blocks. So the key task is first, you need from the address, right? From the address as an input, you need to extract the byte in block bits, the index bits, and the tag bits. Once you have that, you basically can, this L1 and L2 structure is already also built in the starter code. You just need to make sure you maintain, okay, I'm going to put cache block 1 here, I'm going to put cache block 2 here. The read go to the 7 bytes of cache block 1, so you need to return the correct value and things like that. All right, and that's it. And that's it for what you have to do for assignment 4. Any questions? Right now, assignment 4 is due on December 10th. You have close to 3 weeks to work on it. If you have any questions about assignment 4, feel free to let me know. And that's it for the lecture part today.